Hi there, guys. We're going to try and do 12D, the investigation which turns up just before the exercise. Now, what's interesting about 12D, still talking about applying vectors, is that there are no sample questions before you get to exercise 12D. It's just an investigation. And the investigation is what I'm going to go through now on projectiles. This stuff would make an excellent IA. Certainly, there's a lot of maths behind this, which could develop into an IA. A lot of physics in here too. Okay, this investigation is talking about an object traveling under the force of gravity, and they call that object a projectile. For example, they're talking here about a baseball. Okay, but it could be any ball which is being projected. And they're talking about there being an acceleration experienced by the projectile, in this case a baseball, in a downward acceleration of g meters per second squared due to gravity. This acceleration is approximately 9.81 meters per second squared. Now, I know that that's often what you use in physics. You might see some other maths books, they might use 9.8 instead, just to keep it simple. Yeah, and okay, so that's the only acceleration. So let's just have a little look at what's happening here. So let's put it on here. So we're talking not about a case here where we're just throwing something upwards and it's coming back downwards, but we're talking about a case in 2 dimensions, with time being a 3rd dimension, of course, where we're throwing something up and it's reaching some sort of peak and then it's hitting the ground further on as well. And this is your y direction, and this is your x direction. Now, we're assuming that there is no acceleration or deceleration in the x direction. So the ball essentially carries on forever in the x direction. Now, obviously, that's not very realistic, but the slowing down of the ball would probably be quite small compared to the force of the acceleration due to gravity. And also, you'd probably slow down due to air resistance or some sort of friction, whatever it's slowing down with. But those forces we're going to just treat as negligible to keep the model simple in this case. Okay, now if you had a situation where you were just throwing the ball up and down, let's just think about that one briefly. So there's no x component, then you wouldn't need to use vectors. You could just say, I've got this function for the height, which is based on t, and we would know the acceleration in that case. The acceleration would be going in this direction at 9.81 meters per second. That's meters per second squared. So we can write it using the laws of indices like this instead. And so what that's saying is, let's come up with a simple example. If you threw it upwards at a speed of 9.81 meters per second, then after 1 second, it would have reached the top because it's slowing down at a rate of 9.81 meters per second every second. Okay, and after 2 seconds, it would hit the ground again. So it would come back down again. So yeah, that's just kind of a bit of extra detail, really. Yeah. So also, if you have, let's just take some more back. Okay. Also, if you have this situation just on its own, then and not a vector situation, so where you could just set things up in terms of going in along one axis, if you like, then you would also get a graph for that for the height over time. Okay, so there would be your height, and that would be over time, and it would look very similar to this graph, but obviously it's different because this is talking about where we are for every particular time, and this is talking about where we are in time and space, but doesn't give us an indication of the time. Now, you could actually put that on here. You could say, I don't know, this would be our S, our displacement at 0. Maybe this is our displacement of 1 second. This is our displacement at 2 seconds, and so on. So you could potentially put on the timings for this one by putting on crosses, for example. By the way, if you have used the Logger Pro program, which is there's a free sample download of that one on the internet. you will get, and that will track, if you're chucking you're hitting a tennis ball, throwing a ball, or throwing a frisbee, or whatever it is. And Logger Pro will track this in terms of this XY graph here. So it will track things, and it will give you out a table in terms of the time, the X direction, and the Y direction. Okay, so you'll be able to make two graphs from that, or you could maybe make this graph as well. So actually, you could do time versus X, you could do time versus Y, you could do X versus Y. You can make, all different combinations of those things. Right. Okay. So we actually need to get on with this question. Sorry about all the chat. Let's just get rid of that. Let's get rid of some of this. Okay. Right. And I think I'm still missing some of this. Still got some of it here. Let's just zoom out for a second. And let's just take this stuff here and delete it. Sorry about that. Okay. So question 1 says, write down in terms of G the acceleration vector. Right. So in vectors, we want an X direction and a Y direction. So for the acceleration vector, acceleration is going to be, now nothing is happening in the X direction. So we'll have nothing there. There is no slowing down in the X direction, only vertically. And because the acceleration is constant in the vertical direction, we're going to have minus 9.81 here. So y is positive, so because the acceleration is towards the ground, it's going to be negative. They've told us that up is the positive X direction here. Okay, so that's the first bit done. That's your acceleration vector. Right, so then it says at time t is equal to 0, a projectile is launched with a speed of u meters per second. That is a speed of u meters per second. And at an angle of alpha to the horizontal. And it says, find the initial velocity of the projection as a column vector in terms of u and alpha. So let's just have a look at this. What's happening here? So to start off with, we've got, this is our tangential motion at that point. So if you think about our graph, it's like this. So I should be going through 0. We've got some kind of tangent that it's going off at. In this case at the moment. This is the velocity vector which we're looking at, and the velocity vector is going to change in each of these cases here. So we're talking about that initial vector that it's moving with. A change immediately after it started, after you start including some of the acceleration, some of the deceleration, the gravity. Okay, so let's have a look. So we've got alpha here, and we've got the length of u. Now we can see what's happening in the X direction, see what's happening in the Y direction. Now, so this is our X direction, and this is our Y direction. Okay, and in fact, this is actually, let's just go one step further. This is actually your velocity in the X direction. This is the velocity in the Y direction. So an expression for this length here, if we have a sort of look at this, this is our vector. Really shouldn't have drawn it going through the origin. There's our vector there. Okay, and this is the horizontal component of that vector, and this is the vertical component of that vector. Now, if you use SOHCAHTOA trigonometry, we've got SOH, we've got CAH. Okay, so if we use, for example, the cos triangle here, we can see that the adjacent, which would be this, okay, it would be the velocity in terms of the X direction, the X component to that. And so you're going to get there, your adjacent is going to be equal to h. H is the length of this vector, it's u, it's the magnitude, it's the speed. And that's times by cos of alpha. Likewise, if we use the sine triangle, you're going to get u sine of alpha to work out the opposite length. This is the opposite length here, and also this is the opposite length here as well. So that's the vertical component of this. Okay, but if we're going to put that together, well, we can just wrap that up in one vector now. So we can say that v is equal to u cos alpha and u sine alpha here. Sorry about that. Go on, there we go. So there we go. There's our velocity vector in meters per second. Okay. Right. Well, that's actually not dependent on time. So this is actually the instant or the initial velocity here. So we could call that v0. So for example, the velocity vector at time is equal to 1 would be v1. Okay, so find the initial velocity. That's done. We did the previous part as well. And then it says use integration to find the velocity vector for the projection at time t. Okay. So, well, we could just think about this to start off with, actually. I mean, I'll do the integration in a second, but we could think that if this is our initial velocity, we could think, well, in the x direction, nothing is slowing down. There's no acceleration. So the velocity over time here, okay, the velocity dependent on time, we could just call that v if you want. We don't need the t in there, but that's just noting that t is the variable that we're interested in here. So that's v, but it is dependent on time. We'll just call that v if we want to. So we know that the speed is never going to change, or the velocity in the x direction is never going to change, because there's no acceleration in that direction. And we also know that, make this bigger, we know that the initial velocity in the y direction, so u sine alpha, is going to decrease every second by 9.81, so minus 9.81 per second, so times by t. Now, I've not done that, as the question is asked, by using integration, but that is the answer. So now if we use integration, well, how do we use that? Well, first of all, we know that acceleration is equal to dv dt. Okay, it's the derivative of your velocity vector. It is the rate of change of the velocity. Okay, d dt, this part here, is telling us, talking about the rate of change of this thing. So in order to go backwards to get v, you're going to need to do the integral of a, right? So we need to integrate both parts of this. Okay, so if we integrate both parts of this, well, if you integrate 0, you're going to get a constant, because a constant could differentiate to become 0. And I'm going to call that k1 because c1 turns up later. Call that k1. Okay, and if I integrate the second part of this, I've got minus 9.81 t and plus k2. Okay, now you can see how this is similar to this. And since we know that when time t is equal to 0, we have this vector from previously. When you put in time t is equal to 0 in there, that's going to disappear, but we'll still have to get this vector out. So in other words, k1 has got to be equal to this. And since when you put t is equal to 0 in, that's going to disappear, k2 must equal to this. Okay, so there's an alternative way of doing that. I'm running out of space a little bit there, but I really need to write a little note saying when t is equal to 0, we get this out, meaning to say that since this disappears, so when t is equal to 0, this disappears, and this vector has got to be equal to this vector here. Therefore, k1 is equal to u cos alpha, and k2 is equal to u sine alpha. Therefore, this is my final answer. So I'm missing a few little steps there, but I hope you follow that. Okay, so that's part 3 done. All right, well, this is just the first couple of parts. This goes on for a long time. I might need to split this up into 2 or more videos, in fact. Okay, so let's just zoom out. It's pretty tricky to do on this. So let's just zoom in. Might need a couple of goes. Nope. Okay. Okay. See if we can get this. Sorry about this. Okay. Maybe that'll do. Okay. So it says for part 4, it says find the expression for the particle's displacement at time t. So displacement. So we know that displacement or velocity is equal to the derivative of your displacement. Now remember, we're talking in vectors here, so we'll need to differentiate with respect to time this vector of displacement. Now again, if you integrate your velocity, you should get a vector for displacement. We need to do that with respect to time. So we're going to integrate this thing here. So we're looking for a particle, the particle's displacement at time t. So we're going to integrate this thing here, and if we integrate it, now we're doing it with respect to t. So this is a constant with respect to t. Sorry, this here. This is a constant with respect to t because it's not dependent on t. So a constant, when integrated, is going to give us the constant times by t. Now I'm just going to tidy it up by putting the t in the middle. Okay, that's just like saying if I integrated, I don't know, if I integrate 4, it's going to give me 4t. But the constant here is u cos alpha. We're assuming that u and alpha are fixed at the start. There are constants that we're dealing with. Okay, they are not varying in this case because we're looking at t. We're doing this with respect to t. It says here, with respect to t, that's our variable. So that's the first part. Of course, we've got to remember to put on our C as well, and I think because they've already told us here that the at t is equal to 0, the particle has displacement c1 and c2. This is going to become 0 when t is 0, so that's going to leave us with this displacement of c1. That's c1 at the end. That's the constant. It actually matches up with this thing here. Okay, and for the next one as well, we're going to say similarly ut sine alpha. This line here, and then minus 9.81 t squared divided by 2. Okay, so all I've done is I've increased the power by 1 and divided by my new power, and then plus c2. And I know it's c2 because when I put t is equal to 0 in, to here and here, both of these expressions will become 0, and I should be left with c2. If they didn't become 0, then we're not guaranteed that that will be c2. So it's due to the fact that when you put t is equal to 0 in, that these two terms will disappear, and we need to be left with the initial displacement in the y direction. Essentially, c2 is like y0. Actually, we can name this vector something. We can say this was our velocity in the x direction. And sorry, this one is velocity in the y direction. And likewise, this one we can call, this is, let's see if I can just zoom out a little bit. I'm always doing this wrong, you have to zoom at the wrong side. Okay, so this one is going to give you, we could call this one x and y because this is our displacement. Our displacement is actually just our x and y. So we can call that x and y. And if you want, both of those things are dependent on time. Okay, so this is x dependent on time. We could say that's a function of time if we want to as well. We might do that later, but I'm just going to call that x and y just for simplicity there. Okay, so that's finally sorted out question 4. Now guys, this does get more complicated. So let's see, let's deal with the next part. Okay, now if you can, obviously try and do the next part before listening to the explanation. So for question 5, it says use your answer to question 3. Okay, answer to question 3, we're talking about velocity vector, I think, this one here. Yeah, okay, so this one here. So we're using that. Use your answer to question 3 to find the time at which the particle reaches the maximum height. Now, the maximum height is going to be reached when this velocity in the y direction hits 0. Okay, so, you know, in the y direction, you're going upwards, but you're slowly stopping as you're going upwards. It's decelerating as you're going upwards, and then it turns back down and it goes back down to the ground again in the y direction. But at the top of that curve, there is no movement in the y direction, just for a brief instant. So it's slowed down until we've got no movement in the y direction. We still have the same movement in the x direction, but not in the y direction. Okay, so for question 5, we're going to need to say Vy is going to equal to 0. Okay, the velocity in the y direction is going to equal to 0, just for a very short instant at the top. So we're going to say that is equal to u sine alpha minus 9.81 t. Okay, now we need to solve for t because it says find the time at which. Okay, so we need to solve for t. I know we've got u and we've got alpha there. It's like we've got 3 unknowns in this equation, but it's t that we're trying to solve for because they're asking us for the time here. So if we solve that, we're going to get t is equal to u sine alpha, if I take this to the other side, and divided by 9.81. Okay, done. We're told what u is and what alpha is, then we'll know what that time is. Okay, so this one is done. Question 6. Okay, so let's just zoom out again. And let's see if we can zoom in here, give myself a bit of space. Okay, so for question 6, it says use the answer to question 4 to find the expression for this height. Okay, so an expression for this height. So the height when we're at the top, the maximum height in this case. So look at my notes a little bit here. Okay, so yeah, sure. So when we've got, what are we doing? So we've got y is what we're looking for in this question. So use your answer for question 4 to find an expression for this height. So we need to find y when this is our time, because this is the time when it hits the maximum height. So we need to use this part from question 4. Okay, so now we're going to put in ut. Now t is this thing here, so it's going to be a fair bit of algebraic working out here. So let's substitute that in. So we've got our, what should we call this? We call this y max. Is equal to, now we're going to say ut alpha sine alpha. So that's going to give us u squared t sine squared alpha divided by 9.81. Now I'd probably actually, when I'm writing this out, I'd probably use another step here. I'd probably substitute t in first of all to show to the examiner that's what I'm doing, but I'm just making it a little quicker here. Then minus, and then we need to substitute that t in again. So again, I'm going to skip a step here. Okay, we've got 9.81 over 2, and then we've got t squared, so we've got u squared, and then we've got sine squared alpha, so both of the things on the numerator are going to be squared, and then I can see that, then I can see that we've got a divide by 2 coming in here as well, but we also have underneath here this thing squared. So we've got 9.81 squared, and again, I'm just going to make things a little bit quicker here by cancelling one of those 9.81s with the one on top. Okay, so this here is going to simplify to u squared sine squared alpha divided by 2 lots of 9.81. So I'm just going to take that back again. Sorry to be annoying here, but it's so slow for me to write. Let's say we've got u squared sine squared alpha divided by 2 lots of 9.81. So we've got there 19.62. Okay, and I think I've made a mistake there. Yeah, the mistake I've made is when I'm substituting into here, you may have seen that when I substituted in for t needed to disappear there. So I just made a little mistake. I noticed that t was still in there, and we can't have t there, so that needs to just disappear there. Sorry about that. Okay, so let's just check through that one again. What we did is we substituted this into there, so the t disappeared. So I got u squared and sine squared alpha. Sorry about putting the t in there. So that one's got to go. False for that. Okay, so there we go. That's our expression for y max. We answered the question. It says use your answer to y4 to find an expression for this height. Okay, well, we can actually simplify this one as well, because we can see this is both in terms of sine squared alpha. So we've got a constant here of sine squared alpha minus a constant sine squared alpha, and again, u squared is involved in both of those as well. So if you did 1 over 9.81 take away 1 over 19.62, I believe that you get, I did this before, 50 divided by 981 sine squared of alpha. Okay, so that's how it's going to simplify. Am I forgetting? I'm forgetting my u again. Sine squared of alpha at the end. Okay, so there's our expression. We can simplify that one finally as well. Okay, that is done. Question 7 says if the initial speed of the particle is fixed, which value of alpha will result in the particle maximizing the height reached? Okay, so what they're asking is, although this is y max dependent on u and alpha, they're asking an extension question to this one, and saying, well, if u is fixed but alpha isn't, then which value of alpha is going to give us the greatest height? Now, you might be able to think about this one. If you're thinking this object is being thrown upwards, thinking, well, is it going to go, it's going to go kind of like this. So you can see as alpha gets bigger, it's going to get higher, and you can take that to its extreme. And I kind of suspect that when you throw this directly upwards, it's going to reach its highest point. That's what you should do. You should put all your energy into throwing it upwards, not across. So I'm expecting that this is going to come out at 90 degrees. Now, what do we need to do? Well, alpha is now not fixed. It's now a variable in this situation. So we need to find our dy max. I'm just going to call that dy because we've already got the expression for dy max. Actually, no, that's dy max according to t. And we're now going to say, well, what maximizes the maximized height, which was dependent on t? We're now maximizing that as well. So we're going to set this function equal to 0 because we're going to maximize according to we're going to maximize the y max according to alpha. Okay, right. If you want, you can call it just dy d alpha. Okay, so in order to do that, we need to differentiate this thing here. The whole of this is a constant, so we can just put that outside the front. So we've got 50 u squared divided by 981, and then we need to differentiate sine squared alpha. Now, because it's getting kind of messy here, you might be able to do sine squared alpha just in your head, but I suggest that you spend some time just making sure that you're right here and just saying, okay, look, if we have y equals sine squared alpha, or say sine alpha all squared, or let's call that u squared, we can use the chain rule there and say, well, dy d alpha is going to be equal to dy du, which is going to be 2u times by du d alpha. Du d alpha is going to be the derivative of our u, which is sine of a, which is cos of alpha. So we're going to get 2u cos of alpha, Remember, what's u? U is sine of a, sine of alpha. So we're going to get there 2 sine alpha cos alpha. Now I'm going to take all of that back just to keep my page kind of tidy. But that's a little working out which you can do aside. And if you do working out aside, you can always say, doing that on your page, it's not part of the main thing. You can say to the examiner, this is what I'm doing aside. And you can do some big brackets around that working out when you finish with it. Okay, because that's some supporting work, which is showing you the lines of working out here. Anyway, what are we going to do? So we had times by 2 sine alpha cos alpha. You want the quick way of doing that, of course. You say, well, we've got sine squared of alpha here, so we know that sine squared, something squared, is going to be 2 lots of something when we integrate, but then we need to differentiate the function inside as well, which is cos of alpha. So essentially you're getting 2u times by the derivative of the thing which is inside. It's not all that difficult. Okay, so there we go. Are we done with this question? What did the question actually ask? If the initial speed of the particle is fixed, which value of alpha will result in the particle maximizing the height reached? So if the initial speed of the particle is fixed, we haven't done this. We haven't maximized this. We need to equal that to 0. Now, before we do that, I'm actually just going to change this into 50u squared over 981. I'm going to change this using using an identity here, using the identity sine to alpha. You should know that this is equal to this. We did this during trigonometry. This is one of the identities that we've got. I'm not going to go into that right now. Okay, so I'm going to do that because it's neater. And I need to set this equal to 0. Maybe that actually helps with my next part as well. So we're going to set this equal to 0 to optimize it. Now that means that we can just divide by this and that will disappear. Do that because it's a constant. So we just need to solve sine of 2 alpha is equal to 0. Now, if you know your sine graph, you know that sine of what is equal to 0? Sine of 0 and sine of pi, or 180 degrees, or 360 degrees there. So if we undo that on your calculator, you'll get 2 alpha is equal to 0. You'll only get the first of those solutions, meaning that alpha is equal to 0, which is a nonsense, of course, right? Because an angle of 0, if you throw at an angle of 0, you're never going to reach a maximum height. So there's 2 answers to this, in fact. There's 0, well, lots of answers, in fact, unless we restrict our domain for alpha. So we've got 2 alpha is equal to 0, it's equal to pi, it's equal to 2 pi, it's equal to minus pi, and so on. There's loads of solutions for this on the sine graph. Okay, so the other solution for this is going to be when we divide by 2 is pi over 2 and dot, dot, dot. But we found the answer there because the one we want is the non-nonsense answer, which is, and let's just change it back into degrees, alpha is equal to 90 degrees. And that's what we expect. We're happy about that. Throwing the ball directly upwards is going to help it achieve its maximum height. Gosh, that was a long question. Okay, that was question 7. Okay, but we continue. So question number 8, and I'm telling you there's another page of working out here. So stick with it. So it says, use your answer to question 4 to find the time at which the particle hits the ground. The answer to question 4 again, let's just look that back up. We have the expression for the particle's displacement. That is, let's just show you this one again. We're losing things here. This is the answer to question 4. Use your answer to question 4 to find the time at which the particle hits the ground. Now it's going to hit the ground when y is equal to 0. Okay, so we're going to need to set this thing equal to 0. Let me just check my working out with that one as well. Yeah, okay, so we're going to do exactly that. Okay, so let me just zoom out a little bit here. Let's see if I can. So And let's zoom in. Apologies about this being a bit useless. You can't scroll on this thing. So let's have a look at this. Let's actually just change the color of pen so we can see what we're doing. So we're going to do question 8 here, and we're looking now at this thing here for question 8. Just put a little note on that. Okay, we're going to do question 8a. So question 8, we're going to say what's the time when the particle hits the ground? So we need to solve this quadratic equation. Okay, so, and we need to solve for time as well, because it's asking us to find the time at which it hits the ground. So we need to solve that equation. Do we have any other information in this case? Do we know what C1 is? Was there any extra information on this one? I feel like there should be. Use your answer to question 4 to find the time at which the particle hits the ground. I'm feeling like C2 should be equal to 0. Why should C2 be equal to 0? Ah, okay, because I'm missing something here. I'm missing this. Yeah, I thought there was some extra information because we have this extra C2 there, which is going to complicate things no end. So it tells us here that C2 and C1 are basically have got to be 0, because it tells us that this is projected from 0, 0. So C1 is the x direction when t is equal to 0, and C2 is the y direction when t is equal to 0, and we're told that that point is 0, 0. Okay, so yeah, we need to say then, so this was actually from question 4, but there was that new information. It would have been useful if they'd given that information before question 4. So in fact, C1 and C2 in all of the sections after 5 are equal to 0. Sorry to label that point. Now we've got let's just factorize this expression that we have here in green. So let's take out the t, and we've got u sine alpha minus, what's that, 4.905. 4.905. And I've taken out a t. So what I'm doing is I'm just factorizing out the t's here, and I've just divided the 9.81 by 2. T doesn't exist, so I'm going to set that equal to 0. Why am I setting it equal to 0? Because I'm looking for the next time when y, the height in this case, should go 0, 0, when y is equal to 0. So I'm looking for this point here. Okay. And right, so obviously t is equal to 0 is one of the solutions there, and that's the kind of nonsense solution. So we can just ignore that one. And again, I would write that down in an exam situation there, that t is equal to 0 is a solution, but it's not a valid solution. And then we need to solve this bit in the center is equal to 0. Well, if we do that, we're going to get t is equal to u sine alpha divided by 4.905. Okay, that's just solving what's in the brackets there equal to 0. Okay, and that's it. That's done for 8a. Use your answer to find the time at which the particle hits the ground. We have now found the time at which the particle hits the ground. That's good. But then for part B, it says compare your answer to A with your answer to question 5. What does this tell you about the motion of the particle? Now, the answer to question 5 was, let's have a little look at this one, was here. Okay, so there was the answer to question 5. So we're going to try and compare that to this thing here. Now we can see that this answer is twice the size of this answer. If I times the top and the bottom of this one by 2, then I'll cancel the 2 with the 9.81. We'll need to divide that by 2 as well, and I'm going to get out this answer here. So if we just call this one, I don't know, what should we call this, T1, and let's call this one T2. Okay, so T1 is the point at the top. Okay, there's our T1. And the point at the bottom is as a time of t2, and then, I don't know, we could call the time at the start of t0 if we wanted to, we can see that the time at t2 is twice the time at t1. We've got t2 equals 2 lots of t1. And it wants us to interpret this thing here. What does this tell you about the motion of the particle? Well, it tells us that the time to get to the top is the same as the time from the top of the maximum height to the bottom. In other words, this is a symmetrical distribution here. Guys, I'm probably not going to write all of that down, but hopefully you understand that. So, yeah, this is what it tells us, that this is a symmetrical quadratic graph in this case. In fact, we expect it to be symmetrical because there's no deceleration in the x direction. If there was deceleration in the x direction, then it's probably was going to confuse things. So it's going to be a more sophisticated model. But yeah, so it's telling us that the time taken from 0 to the top is the same as the time taken from the top back down to a height of 0. You need to put that in words. Because it takes me so long to write it, I'm not going to write it here, okay? Okay, now it says the range of the particle is the total horizontal distance traveled until it returns to the same height as that at which it began. So it's now, we found the time that it's taken to get to this point where it hits the ground. Now they're saying the range, a bit like what we normally call the domain on the x-axis. So the range of the particle is the total horizontal distance. So they basically just want this distance here. So we're going to put t is equal to 2 back into the x direction up here. Okay, where c1 is equal to 0. Now we know that we start at 0, so all we really need is the distance when we've got this t2 time. Okay, so now again, because it's getting a little messy, I'm just going to switch pen color here. So what we're trying to do for question 9 is we're putting in to x, let's say x is a function of t here, and we're going to substitute in t2, so we're going to put in t2, put in t2 to x, and we know that c1 is equal to 0, so we're going to have u lots of this thing here. So that's going to be u squared sine alpha over 4.905. Okay, and then so I'm putting into this section here, and we know that c1 is equal to 0. Should put in, this is question 9 we're using this for. So I'm going to put in c1 is equal to 0. I think we've done that now. Put in t2. We've done everything. Oh, we're missing cos alpha. So times by cos alpha. Okay, so that's an expression. We probably want to tidy that one up a little bit. In fact, think about how we can tidy that one up. If we times the top and the bottom of that one by 2, then you're going to get 2 lots of this. On the bottom, you're going to get u squared over 9.81. We're going to get that back again. Now, if I times the top by 2 as well, then it's going to bring me back to that to this expression here. So we're going to get sine of 2 alpha, same identity that we're using from before. So this one and this one here. Okay, so that's our expression. Yeah, that's done. Find an expression for the range of the particle, and we're done with that one. So question 10, it says find the initial speed of the particle. Sorry, if the initial speed of the particle is fixed, which value of alpha will result in the particle maximizing its range? So if the initial speed of the particle is fixed, so this is now fixed, and we're going to sorry, U is now fixed, and now we're looking to maximize its range. Okay, so this then is a constant, and let's differentiate this thing here. So now let's, for question 10, let's give ourselves a little bit more space here again. And okay, let's just zoom out there and zoom in here. Okay, so question 10, sorry. Pretty tricky to do this. I don't know why they make it so hard. Sorry that the writing is so small, but I read it out again. It says if the initial speed of the particle is fixed, which value of alpha will result in the particle maximizing its range? So we need to do dx d alpha. Okay, now I could call that dx in brackets t2, just as I did up here with y max, but I'm just going to keep it simple like that. And then I'm going to differentiate this thing. Now we've got a constant in front, 9.81. So that's our constant. And now we're going to differentiate this thing. Now, again, you could use the chain rule here, but it's pretty simple on this one. So sine becomes cosine of 2 alpha. And the derivative of the thing which is inside with respect to alpha is going to be 2. So there we go. There's our expression. And that's question 10. Anything more that we need to do there? So yeah, okay. So just we need to say then that the initial speed of the particle is fixed. So the maximizing this, to maximize this, we can equal this to 0. Now we could simplify that if we wish to, but I'm just going to spare you that. So we could simplify that a little bit. But in fact, seeing as all of this is a constant, and we can divide by that constant when we're equaling that to 0, and then we're going to get cos of 2 alpha has to be equal to 0. Okay, now what's the answer to that? So for cos of 2 alpha is equal to 0, where does cos equal to 0? We've got this point and this point. So that's going to give us pi over 2, or 90 degrees, and 270 degrees. So 270 is going to be out of the range, which is useful for us. If we're throwing this thing originally at an angle between 0 and 90 degrees. So 2 alpha is going to be equal to 90 degrees, or pi over 2, which means that alpha is going to be equal to 45 degrees. So to maximize the range, we need to throw this object at 45 degrees. That's a pretty nice result. So to get it the furthest, we don't throw at 30 degrees, we don't throw at 70 degrees, we try to throw at 45 degrees. And that has a practical implication for sports as well. Trying to throw at, in this model at least, where there's no slowing down of the ball, we need to throw at 45 degrees. No slowing down of the ball in the X direction. Okay, so that's question 10, sorted. Phew. Okay, so there's actually more to this. Let's just zoom out over here and let's zoom in to this one here. So, and let's just zoom out here. And well, that'll do. So number 11, it says a ball is projected from the ground. So it's now giving us some information here. It's saying that ball is projected from the ground at an initial speed of 15 meters per second and an angle of 30 degrees. So all we need to do now is use the formulas which we've previously been working with. So this is a concrete example, and they're asking us, first of all, for 11, find the horizontal distance traveled. So for the horizontal distance traveled, we need to find the range, and the range was given by u squared. So this is from question 9. So this is question 11 here. So the range, let's take that back. Question 11. The range came from question 9. That's equal to u squared sine 2 alpha divided by 9.81. Now, if you substitute in your two values, so if you substitute in 15 and 9.81, then you're going to get, and the angle of 30, messing up a bit today, sorry about that. We've got 15 squared times by sine, 2 lots of 30 degrees. Make sure that your calculator is in degrees, and divided by your 9.81. So that's not 9.81 here, that's 9.81 from the model which we've developed based on that. Okay, and then that's going to give us a range of, if you work it out, perhaps you already know that sine of 60 degrees is √3/2. That's one of your exact ratios. If you work this one out, you get 19.8629 ... meters, and you can round that off to whatever accuracy that you need. Probably 3 significant figures would be useful. You might want to store that on your calculator for the time being. For question 12, okay, so this is becoming very practical here. Now found the range of this particle. So for question 12, find the maximum height reached by the ball. The maximum height we found in question 10. We found we found the height formula came from S. So remember, we had S was based on X and Y. So we'll now need Y dependent on this, dependent on the maximum height times, trying to think where that is. So we're going to need Y dependent on the maximum time at which the maximum height was achieved. Now, I think that was U sine alpha over 9.81. Okay, so that's U sine alpha over 9.81. So that was the time, that was the expression in terms of A and U for the time at which we reached the top point of this curve. And I'm saying Y here as a function of that time. We called that time 1 earlier on. Okay, so there we go. That was time 1 when we hit the top. Now into Y, well, Y actually had a function as well. If you remember, Y was equal to minus 9.81 t squared over 2 plus ut sine of alpha. Now that came from way back when, I think maybe question 4, where we worked out the displacement vector. So we're taking here the y from that displacement vector. Okay, and now we need to substitute in for this t. So the t needs to be replaced by this thing here. Now, just a tip on your calculator here, to stop you from writing out quite so much, what I would do here is substitute my u and my alpha into here, and I would store it on your normal basic Casio calculator. I would store it as A, and then when we come back to trying to work out this, you can then just put in alpha A when you're doing this. So you can replace all this with just A. It's going to stop you from writing it out twice. Okay, now if you do that, if you put in U, if you put in alpha, if you substitute it into this thing here, missing a few steps here really, just for brevity, that gives you the answer of 625 over 218. And I'm expecting a lowish answer, probably less than 5 meters high, if this is how far it's got. So if we then just work that out on the calculator, that's going to give us an answer of 2.86697 ... meters, and of course you can give that to whatever accuracy is needed. So a little under 3 meters, given these conditions here, throwing it at a speed of 15 meters per second at an angle of 30 degrees, we're getting to a height of around 3 meters, just a little less than 3 meters high, and we're getting to a range we're able to get it to 19.9-ish, 20 meters. Okay, so on those conditions, and essentially, if you're able to throw at a maximum speed of 15 meters per second, if that is your maximum speed, then and if you always throw it at 30 degrees, then you're going to get this range, and you're going to get this height. Okay, so that X range, X distance, and this height before it hits the ground the first time. Phew, that was epic. Thank you for bearing with me and dealing with all of my ums and ahs through that one, because it's quite difficult to organize. Okay, so for 13, it says in a more realistic model, what additional force will need to be taken into account when predicting the flight of the ball. So perhaps air resistance will be taken into account there. And you might like to know that normally we use a formula in physics to say that your velocity in the X direction would be dependent on the resistance would be dependent on the square of the velocity. Okay, so that would help make a more sophisticated model, but we're not going to deal with that just now. Okay, and 14 and 15 are just discussion points here as well. What does the common vector describe in projectile motion? Well, you can answer that one. It's giving us it's breaking down our speed or our velocity into X and Y components. A column vector could be for the velocity, it could be for the displacement, it could be for the acceleration. But in each of those cases, it's splitting things down into, say, for example, displacement, it would be splitting it down into X displacement and Y displacement. So it's splitting it into two components in the two directions. And so for 15, it says, how are vectors useful in describing projectile motion, and how do we find the velocity equation? Well, hopefully you've seen that it's been useful when we're able to make these predictions here for essentially what's the furthest you can throw a ball. That would be a useful thing. If you're able, for example, to throw at, let's say, 20 meters per second, then you can find the maximum angle or whatever. Okay, you can use this in practical situations. Okay, thanks for listening. It's been epic, and yeah, good stuff. Well done for getting through that one.